Implications of a semi-empirical planetary temperature model for a new understanding of Earth's paleoclimate history and polar amplification. This presentation introduces a new theoretical framework to explain past climates using system-level relationships inferred from NASA planetary data. Hello, my name is Nikolov. I'm a physical scientist with the U.S. Forest Service. I list my affiliation here as an independent researcher because this study was conducted outside of my regular work hours as a government employee. I was instructed by my employer to separate my curiosity-driven inquiry into climate processes from taxpayer-funded fire weather research I conduct at my office. My co-author, Dr. Zeller, on the other hand, is a retired Forest Service physical scientist with no restrictions, as can be seen on this photo. Since this talk is about a new geophysical paradigm of climate change, I encourage you to pause the video whenever you need extra time to examine a slide in greater details. Also, watching this presentation more than once, along with a proper review of key references mentioned here, is highly recommended for a full and adequate grasp of this new concept. The purpose of this talk is twofold. First, present a novel semi-empirical model that accurately describes long-term average surface temperatures on rocky planets and moons over a broad range of physical environments in the solar system. Second, discuss implications of the new model for advancing of our understanding about drivers of Earth's paleoclimate. We based our approach on the premise that processes creating a pattern of planetary temperatures across space in the solar system must also control the dynamics of surface temperature over time on individual planets and moons. This notion follows from a fundamental postulate in physics that the laws of nature are invariant across space-time. It means that relationships inferred from spatial analysis of parameters along large environmental gradients can be applied to study the temporal dynamics of such parameters at points in space. Guided by this principle, we assembled a dataset of planetary climates from the peer-reviewed literature that covered a broad range of physical conditions in the solar system and was represented by 3 planets and 3 moons with rocky surfaces and available high-quality measurements of ground temperatures and atmospheric properties obtained during the past 40 years. These planetary bodies are Venus, Earth, Moon, Mars, and Triton. Collectively, they cover surface temperatures from 39 degree Kelvin to 737 degree Kelvin. Top of the atmosphere solar irradiance is from 1.5 watts to over 26 watts per square meter, and a giant gradient of atmospheric compositions, pressure, and density. In an effort to identify common drivers of global surface temperature across the 6 planetary bodies, we subjected the above dataset to dimensional analysis, or DA for short. Dimensional analysis is an objective engineering technique employed to derive physically meaningful relationships from measured data without prior knowledge of any underlying theory about a studied phenomenon. Hence, DA can assist the development of new physical theories. Our application of dimensional analysis led to a surprising discovery about the physical nature of the atmospheric thermal effect, also known as greenhouse effect, theretofore unbeknown to science. This 2017 paper describes our data and methodology as well as the results obtained therefrom. Briefly, we found that across diverse planetary environments, the atmospheric thermal effect is a form of adiabatic heating, also known as compression heating, caused by total air pressure and having no dependence on atmospheric composition. This finding has several fundamental implications for the current climate theory, one of which is that infrared back radiation, also known as greenhouse radiation, is a byproduct, meaning a consequence of the atmospheric thermal effect rather than a driver of the global surface temperature as assumed for over 150 years. According to our results, the downwelling long-wave radiation is globally affected by climate change, but it does not control the global climate. I encourage everyone interested in this topic to carefully study this paper since it provides the basis of our new concept about drivers of Earth's paleoclimate discussed here. This plot depicts the single most important results from the dimensional analysis of NASA planetary data described in our 2017 paper. The relative atmospheric thermal effect, or rate for short, defined as a ratio of planet's observed long-term global surface temperature under an atmosphere to the planet's hypothetical surface temperature without an atmosphere, is completely determined by the mean atmospheric pressure at the surface. This is represented by the red curve derived from planetary data using nonlinear regression analysis. This curve puts Earth in the context of a cosmic continuum of climate drivers with no visible tipping points. Our dimensional analysis also included concentrations and partial pressures of greenhouse gases as potential predictors, but these did not produce physically meaningful relationships with surface temperature, and most importantly, failed to describe a continuum across the planetary bodies. Note that while the relative atmospheric thermal effect depends on pressure, the absolute atmospheric thermal effect depends on both pressure and top of the atmosphere solar irradiance. You might ask, how does one estimate the no-atmosphere global temperature of a rocky planet, provided that it is not an observable quantity for bodies with atmospheres? This 2014 paper describes the derivation of a physics-based formula for calculating the average temperature of airless bodies using analytical integration of the Stefan-Boltzmann radiation law over a sphere that accounts for daytime storage of solar energy in the regolith and the subsequent release of such energy as heat at night. The new airless temperature formula, shown on the next slide, was validated against recent NASA thermophysical measurements and model simulations for the Moon. This paper also explains why the canonical 33-degree estimate of Earth's greenhouse effect is mathematically and physically incorrect. It is shown that the actual thermal effect of Earth's atmosphere is about 90 degrees or 2.7 times greater than assumed for over 100 years. Please review this publication for further details. This is the general equation describing the long-term or baseline global average surface temperature of rocky planets and moons, T sub SB. It is a product of two terms. First, the body's no-atmosphere temperature, T sub Na, marked in yellow. And second, the relative atmospheric thermal enhancement due to pressure, E sub A, marked in blue. Since the no-atmosphere temperature depends chiefly on top of the atmosphere solar irradiance, the baseline global temperature is ultimately a function of planet's mean surface atmospheric pressure and distance from the sun. This is a 3D rendition of the simultaneous dependence of a planet's baseline global temperature, T sub SB, on solar irradiance and atmospheric pressure according to our model. Note that the global temperature increases non-linearly with both solar irradiance and atmospheric pressure, but is more sensitive to incoming shortwave radiation than to pressure. That's because atmospheric pressure does not add energy, external energy to the system, but only adiabatically enhances the energy received from the sun through force. Remember that pressure is defined as a force applied to a unit area, and that energy, and therefore temperature, cannot exist without a force. Even electromagnetic radiation has a measurable pressure when viewed as an energy flux. I used the term baseline temperature a few times before, but what's the Earth's baseline temperature? This slide illustrates the concept using two recent global temperature reconstructions. The baseline temperature is the long-term semi-stable value depicted with the dashed regression lines on both plots. Although these reconstructions employed disparate methods that yielded vastly different patterns of interannual variability and centennial cyclicity, the 1,000-year baseline temperatures are remarkably similar between the two time series and only differ by about 1/4 of a degree. These plots suggest that Earth's baseline global temperature for the past 1,000 years is around 286.4 Kelvin or 13.2 degrees Celsius. Decadal fluctuations of the global temperature around this baseline are relatively small and will not be discussed here because they are caused by changes of cloud albedo, which is a topic of another talk. If solar irradiance and mean surface pressure determine a planet's baseline global temperature, as we already discussed and was found by Nikolov and Zeller, do these forcing factors also set planets' average latitudinal surface temperatures? To answer this question, we analyzed data from 4 planetary bodies that had sufficient observations available to allow the calculations of continuous latitudinal temperature profiles shown on the next slide. Although Venus had good observations as well, we decided to preserve it as an independent test case because the surface of Venus is practically isothermal. After determining the mean temperatures at several absolute latitudes for each body, which were equator, 20 degrees, about 38 degrees, 60 degrees, 75 degrees, and 90 degrees latitude, we calculated the temperature differences between each latitude and the global mean. The polar temperature was linked to the equatorial temperature via the observed equator to pole temperature gradient, which we hereafter call meridional temperature gradient, or MTG for short. In this way, all latitudinal temperatures were tied to the global average temperature. We then ran a dimensional analysis to identify common predictors for the calculated latitudinal temperature gradients across the 4 planetary bodies. We found that these gradients were, when normalized by the no-atmosphere temperature of each body, were closely related, albeit in a nonlinear fashion, to the average atmospheric molar density of the surface, which depends, of course, on total pressure and global temperature according to the gas law. The close relationship between normalized latitudinal temperature gradients and atmospheric molar density makes perfect physical sense because gas molecules are the principal carriers of heat in the atmosphere, and a mole of any gas contains the same number of molecules specified by the Avogadro's constant. Thus, the higher the air molar density, the more heat carriers are available per cubic meter to advect energy horizontally, hence reducing the relative size of latitudinal temperature gradients. Since the no-atmosphere temperature of a planet depends on solar irradiance, the absolute latitudinal temperature gradients become functions of atmospheric molar density and top of the atmosphere solar irradiance. Shown here are observed latitudinal temperature profiles of the 4 planetary bodies used in our analysis. Note that Titan has the smallest equator to pole temperature gradient of only 3.7 Kelvin because of its relatively high atmospheric density and a great distance from the Sun. Our Moon has the largest MTG, about 130 degree Kelvin, due to its closeness to the Sun and a lack of an atmosphere. Earth's atmosphere reduces our meridional temperature gradient to about 36% of Moon's MTG. This is the functional relationship between normalized meridional temperature gradient and atmospheric molar density across the 4 planetary bodies. The plot on the left uses inverse normalized MTG and logarithmic axis to facilitate the nonlinear curve fitting. The plot on the right shows the MTG response on linear axis. As one can see, the relationship is strongly nonlinear. This is the regression equation describing the curve on the right plot. The second line in this equation expresses the molar density via the surface pressure and average global temperature using the ideal gas law. This formula reveals that the absolute meridional temperature gradient measured in Kelvin depends ultimately on solar irradiance and atmospheric pressure. This is a 3D rendition of the simultaneous response of MTG to solar irradiance and total pressure described by the equation on the left. Note that MTG increases with solar irradiance and decreases with pressure in a nonlinear fashion, which creates the peculiar convoluted shape of the MTG response surface. According to this data-driven model, large MTGs are to be expected on bodies that orbit close to the Sun and have little or no atmosphere, such as Mercury. Small to zero MTGs are to be found on bodies with massive atmospheres, such as Venus, or those orbiting far away from the Sun, such as Titan, Triton, and Pluto. Our model predicts a zero MTG for Venus in agreement with observations for that planet. As we'll see later in the discussion, the strong dependence of MTG on total pressure revealed by the NASA planetary data is key to understanding the polar amplification in Earth's geological record. These are two additional examples showing normalized latitudinal temperature gradients as functions of atmospheric molar density inferred from NASA data, one for the equator and another for the 60-degree latitude. Similar relationships were derived for 20-degree and 75-degree latitudes. The evidence presented thus far clearly shows that long-term latitudinal temperatures on rocky planets are fully predictable from the amount of solar radiation reaching the top of the atmosphere and surface air pressure. As long as planets' distance from the Sun and total atmospheric mass stay constant, the baseline surface temperature would remain stable. That's a key conclusion. Alternatively, a change in either atmospheric pressure or top of the atmosphere solar irradiance would alter not only the global baseline temperature of a planet, but also the entire surface temperature field by shifting latitudinal temperature gradients. Thus, our model mathematically captures the physical interconnectedness between global average temperature and mean latitudinal temperatures. We now ask the question, can a model derived from NASA planetary data that cover a huge range of physical environments in the solar system shed new light on the drivers of Earth's paleoclimate? Before delving into this question, it might be informative to take a quick look at the best available proxy-based record of global surface temperature and atmospheric CO2 concentration for the past 83 million years shown on this plot. Note that these are independently reconstructed time series using non-overlapping proxies. Therefore, these records offer an objective basis for reaching conclusions about the CO2 temperature relationship on geological timescales. A cursory examination of the two records reveals that pre-industrial CO2 concentrations of less than 300 ppm are found during both glacial periods of the last 1 million years and warm, ice-free climates of the late Cretaceous, some 70 to 66 million years ago. Also, for tens of millions of years since the Middle Eocene, CO2 and global temperature appear to have followed divergent trends. Such mismatches cannot be explained by the greenhouse theory of climate change. These observations suggest that CO2 was likely not a driver of Earth's paleoclimate during the Cenozoic and beyond. To investigate the potential implications of the NZ planetary temperature model for a new understanding of Earth's paleoclimate, we used a three-step method outlined by Richard Feynman in a famous lecture at Cornell University in 1964, where he said, "First, we make a guess. Then we compute the consequence of the guess to see what it would imply if correct. And finally, we compare those computation results to nature or observations. If the results disagree with observations, then our guess is wrong. If they agree with independent measurements, then our guess or hypothesis are correct." We came up with the following hypothesis. Observed changes of Earth's global baseline surface temperature on timescales of thousands to millions of years are caused by variations of total atmospheric mass and surface pressure rather than greenhouse gas concentrations. This is based on an insight from our semi-empirical model that if Earth's distance to the Sun has been stable for the past 250 million years, as indicated by the best available orbital models, for example, Laskar et al. 2011, then changes of Earth's baseline temperature could have only been caused by variations in mean surface atmospheric pressure. What are the consequences of such a guess, or how can we test our hypothesis? According to relationships in our model derived from NASA planetary data, surface atmospheric pressure is a major controller of the meridional temperature gradient. Therefore, temporal variations of mean surface pressure should produce polar amplifications that could be compared to geological records. How do we verify this? Well, if our pressure-driven model correctly reproduces independent reconstructions of equatorial and polar paleotemperatures, then the above hypothesis should be considered validated. It is important to point out here that simulating the correct size of past polar amplification has been a long-standing challenge for climate models. This figure shows the evolution of Earth's global surface temperature for the past 83 million years, according to the best available proxy-based records. The resolution of the time series varies depending on the geological period, but is never finer than 1,000 years. Hence, this is a record of Earth's baseline temperature variations through geologic time that is suitable for investigation using our planetary temperature model. We will test our hypothesis about pressure being the driver of Earth's paleoclimate for two climatologically contrasting periods: the early Eocene, about 51 million years ago, and the late Quaternary, spanning the past 780,000 years. In the early Eocene, the global baseline temperature of Earth exceeded 29 degrees and there was no ice on the planet. During the late Quaternary, the global baseline temperature fluctuated between 7.2 and 15 degrees Celsius, with a long-term average hovering at about 10.5 degrees, and large continental glaciers covered higher latitudes most of the time. We'll also briefly discuss the Paleocene-Eocene thermal maximum that occurred some 56 million years ago. These plots show polar amplifications found in the geological record that our planetary temperature model should be able to reproduce if Earth's paleoclimate was indeed driven by changes in surface atmospheric pressure. The figure on the left compares latitudinal temperature profiles between early Eocene and the present. Notice that while 51 million years ago the tropics were only 9 degrees warmer than today, polar temperatures were almost 38 degrees higher than the present. The figure on the right depicts dynamics of polar and equatorial temperature anomalies for the past 780,000 years. While equatorial temperatures fluctuated 3 to 5 degrees Celsius between glacial and interglacial periods, polar temperatures oscillated 10 to 13 degrees. The light blue shaded area highlights the polar amplifications that the NZ model will be tested against. On this slide, the figure on the left depicts two recent reconstructions of the global baseline surface temperature dynamics for the past 780,000 years. The resolution of both time series is 1,000 years. We averaged them out to come up with a good central estimate of Earth's temperature dynamics during the late Quaternary, which is shown on the right. The average time series was then fed into an inverted version of the NZ global temperature model that computes atmospheric pressure from temperature. Model inversion was achieved through an iterative numerical procedure that guarantees high precision of the results. Here, the figure on the right shows the expected dynamics of mean surface atmospheric pressure if glacial interglacial cycles were caused by pressure changes. As explained earlier, this pressure series was calculated from the global temperature record on the left by inverting the NZ model. Next, we ran the extended NZ model using time series of observed global temperature and simulated pressure, shown here, to predict the dynamics of equatorial and polar absolute temperatures for the past 780,000 years. These model results were then compared to published independent reconstructions of tropical and polar temperatures. This is the result of the model data comparison of absolute equatorial and polar temperatures for the Quaternary. As you can see, the model performed remarkably well. This slide shows the same model data comparison, but in terms of temperature anomalies from the present. The model predicted almost perfectly the observed polar amplifications during the late Quaternary. This is in stark contrast to CO2-driven paleoclimate models, which predict a very small variation in the amplitude of temperature fluctuations between tropics and the poles during the glacial cycles. A scatter plot of observed versus modeled polar temperature anomalies shows a significant skill of the NZ model in simulating the polar temperature dynamics during the late Quaternary, while assuming that glacial cycles were driven by changes in total atmospheric mass and surface pressure. Testing the NZ model for the early Eocene produced equally impressive results. Proxy-based temperature reconstruction yielded a global average sea surface temperature of 31.6 degrees Celsius for the early Eocene, estimated by spherical integration of the median sea surface temperature curve, shown as dashed blue line on this plot. According to the NZ model, this global temperature requires a mean surface pressure of 277 kilopascal. Using this pressure value and a top of the atmosphere solar irradiance suitable for the early Eocene, the NZ model predicted a latitudinal temperature profile, shown here in red, that is very close to the proxy-derived median sea surface temperature and well within the 90% confidence interval of the reconstruction. In contrast, CO2-forced paleoclimate models, represented here by their ensemble mean in dark gray, failed to reproduce the observed high latitude warmth of the early Eocene. If pressure changes can explain so well observed polar amplifications during the late Quaternary, which is the last 780,000 years, and early Eocene about 51 million years ago, it is only reasonable to assume that a drop of surface pressure due to loss of atmospheric mass to space was also responsible for the observed 20-degree cooling during Earth's transition from a hot house to an ice house over the past 50 million years. This is the model dynamics of mean surface atmospheric pressure that would explain global temperature changes observed in the geological record over the past 83 million years. It was produced by numerically inverting the main equation of the NZ model and solving it for pressure while using the global proxy temperature record as input. From a standpoint of our discovery about the atmospheric thermal effect being a form of adiabatic or pressure-induced heating, this evolution of surface air pressure is the only physically plausible mechanism that could explain observed changes in global and latitudinal temperatures during the Cenozoic and beyond. Such a dramatically different atmospheric dynamics from what has been assumed in paleoclimatology and paleontology thus far would have profound implications for our understanding about the evolution of geophysical environments and life on Earth. As explained earlier, according to our model based on NASA data, global pressure variations imply changes of meridional temperature gradient. Shown here are the model dynamics of the meridional temperature gradient for the past 83 million years, resulting from predicted pressure changes on the previous slide. The graph on the left suggests that past equable climates on Earth were caused by high atmospheric pressures resulting from increased atmospheric mass, possibly due to heightened rates of mantle degassing. Note that for the Paleocene-Eocene thermal maximum some 56 million years ago, the model estimates a reduction of Earth's meridional temperature gradient to less than 16 degrees Kelvin, compared to the 46.5 degree at present. We will return to the PATM hyperthermal a little bit later. This plot depicts model temperature dynamics at the equator, 60-degree latitude, and the poles for the past 83 million years. The time series shown at 38-degree latitude is the reconstructed proxy-based global temperature, which corresponds to the temperature evolution at mid-latitudes. Again, predictions made by our model for the above latitudes are based on a single assumption that observed changes in the global average temperature were caused by variations in surface atmospheric pressure, which also implies changes in the meridional temperature and other latitudinal temperature gradients. Note that simulated annual polar temperature starts falling below the freezing point of water around 44 million years ago. The model predicts intermittent subfreezing periods at the poles between 44 and 36 million years ago, and a permanent subfreezing environment after 34 million years ago. The projected timing of initial polar glaciation at around 44 million years ago followed by a period of episodic glaciations until 34 million years ago, matches quite well results from an independent recent study by Tripathi and Darby 2018 on the history of Greenland and Arctic glaciations based on measurements of ice-rafted iron oxide grains in ocean sediments. This is the paper by Tripathi and Darby 2018 providing independent confirmation of our model projections about the evolution of polar temperatures from the Middle Eocene to the early Oligocene, 44 to 34 million years ago. Another successful projection by our NZ model involves the peak polar temperatures during the Paleocene-Eocene thermal maximum, the most extreme hypothermal of the past 250 million years ago, which occurred 55.9 million years ago and only lasted less than 200 years. Our model estimated annual mean polar temperatures in excess of 23 degrees Celsius during the PATM as a result of a projected 380 kilopascal mean surface pressure. This temperature prediction matches well reconstructed temperatures from a marine sedimentary sequence at an Arctic drilling site located at about 88 degrees north. Note that this 2006 paper also points out the inability of CO2-driven climate models to reproduce the observed extreme polar warmth during this hypothermal. Standard models underestimate peak PATM polar temperatures by more than 10 degrees. In conclusion, top of the atmosphere solar radiance and total atmospheric pressure completely and accurately explain the latitudinal patterns of mean planetary surface temperatures across a broad range of physical environments in the solar system. This confirms the previous finding by Nikolov and Zeller 2017 that long-term planetary temperatures are independent of atmospheric composition. The NZ planetary temperature model derived from recent NASA observations provides a new, simpler, and more accurate explanation of the observed global and latitudinal dynamics of surface air temperatures throughout Earth's geological history. On a timescale of thousands to millions of years, Earth's climate appears to be driven by variations of total atmospheric mass and surface air pressure, a mechanism poorly understood at present and not considered by the greenhouse theory. This introduces a new paradigm of understanding about drivers of Earth's climate. The ability of the NZ model to correctly reproduce independent measurements of past equatorial and polar temperatures confirms the physical nature of the empirical pressure-temperature relationships inferred from NASA planetary data. Thank you for watching. I understand this is a new paradigm, but if you have questions, please feel free to email us at nnikolov02@gmail.com.